Welcome friends to this NPTEL online certification course of environmental soil chemistry, and today we are going to start week 9 or module 9, and in this week we will be basically talking about pollutants and soil solution interactions. So, if we just go ahead and see what are the concepts we are going to cover in this. So, in this lecture, in this week we have covered these following concepts. First of all, we will be talking about the pollutants in soil solution, what are the major pollutants and how they interact in the soil solution. Then we will be talking about solubility equilibrium. Some of the solubility equilibrium we have already covered in our previous lectures. However, we will be covering some more in this week, and after that we will be talking about solvents and surfactants interactions, and next we will be talking about acid rain formation as well as gypsum dissolution in alkaline soils. Then we are going to cover one of the most important aspect, that is sewage sludge and its impact on soil pollution. And then we will be talking about complex formation with organic matter, specifically in terms of heavy metals, and we will be also talking about solubility of polycyclic aromatic hydrocarbons, which is considered as one of the major pollutant in soil. So, these are the several important concepts which are basically covered in this week and in this module, and we are going to discuss them one by one. So, let us start with the first concept, that is pollutants in soil solution. So, soil systems comprises a dynamic and complex array of inorganic and organic constituents. The concentration of pollutants in the soil liquid phase is governed by a series of reactions. So, what are those reactions? There are 5 major types of reaction. First of all, acid base equilibria reaction, then oxidation reduction equilibria reaction, then complexation with organic and inorganic ligands, precipitation and dissolution of solids, and ion exchange and adsorption. Now, among all these we have already covered in details about oxidation reduction equilibria or redox potential. We have also covered in detailed discussion about ligands and complexation with organic and inorganic ligands, and also we have extensively discussed ion exchange and adsorption in our previous weeks. So, here in this week we will be basically talking about in details about acid base equilibria, and also briefly we will cover the precipitation and dissolution of solids. So, among all these 5 reactions, we are going to discuss only this number 2, that is number 1, that is acid base equilibria, and number 4, that is precipitation and dissolution of solids. So, remember that the rates at which this reaction occur with the rates of degradation of biological uptake control the concentration of the pollutants in the soil liquid phase. So, basically the rates at which this reaction occurs, that means the reaction rate controls the concentration of different pollutants in the soil liquid phases. So, if you see the interaction between free pollutant concentration in soil solution and how they change in the soil solution, how their dynamics change in soil solution, these diagram will help you to understand it clearly. So, let us consider this is basically the interaction between the reaction and soil system and the soil solution. So, if you can see here, there are free pollutant concentration in the soil solution. So, let us consider it can be anything, it can be either organic or inorganic. So, this free pollutant concentration in soil solution can either go to complex formation, and from the complex also it can go to the free pollutant in soil solution pool. Apart from that, it can also take part in acid base reaction, and this reaction is basically both way reaction. So, basically from here also they can go to free pollutant pool in the soil solution. Further, this free pollutant concentration in soil solution can produce the precipitation and also dissolution of the solids, and this is also a both way reaction. So, apart from these three, we can see the pollutant must transfer from this free pollutant concentration in soil solution, which is which is also both way reaction. So, all these reactions which you are seeing in this diagram are going in both direction. Apart from that, they can go to the ion exchange and adsorption reaction can show, and from the adsorption, when resorption occurs, they finally go to the free pollutant concentration in soil solution again. And apart from that, that also these free pollutant contained in the soil solution can also impact the redox reaction and vice versa. So, these are the snapshot of interrelations between the reactions in the soil system and the soil solution. So, I hope this is clear to you guys. So, let us move ahead and see what is the interaction between the heavy metal pollutants in soil solution. So, if we consider there is a precipitation in the soil surface, this water basically moves from the soil surface through the process of infiltration, and the soil composition, soil reaction, redox condition and reaction kinetics, all of these can impact the conversion of the metal cations in the aqueous form, and they can interact with different organic matter and inorganic fractions. Ultimately, after these reactions are taking place, they can ultimately convert it to new convert to new species and ultimately go to the groundwater, and also from the groundwater also they can move up into the soil. After different types of fates of these positively charged heavy metal cations, they can be either uptaken by the plants, or they can be immobilized, or they can be uptaken by different microorganisms. So, there is a you can see there is a interaction going on between these microorganisms, heavy metals as well as the plants. So, this way the heavy metals can be uptaken by plants and microorganisms. These heavy metals can react with different inorganic components, produce the metal compound. They can sorb into the organic matter, which we are going to discuss in our coming lectures. So, they can produce the organic matter metal complexes, and also they can sorb to other species. So, this is the basically the interaction of heavy metal or dynamics of heavy metals in the soil solution. So, heavy metal pollution, as far as the Indian soils and Indian heavy metal concentration and are in soil and groundwater are concerned, this figure shows a important insight of how many districts of India are affected by specific inorganic pollutants. So, if you see the nitrates, you see that 386 districts are affected by this nitrate pollution, and the affected states or union territories are a total of 21. In case of fluoride, 335, and the number of affected states or union territories are 20. Iron contamination can be found in 301 districts and 26 states or union territories. Salinity problem is prevalent in 212 affected districts or 15 affected states or union territories. Arsenic problem is prevalent in 153 districts and 21 states or union territories. Lead, which is another very important heavy metals as far as the potential contaminants are concerned. So, lead showing the they affect 93 number of districts and 14 states or union territories. As far as the chromium is concerned, this chromium is affecting 30 districts and as well as 10 states or union territories. Cadmium cadmium pollution can be found in 24 districts and 9 states or union territories. So, you can see as far as the total number of districts are concerned which are showing different types of heavy metal pollutions or inorganic pollutions are a total of 780. And remember that among all these different elements, inorganic elements, this lead, cadmium and chromium are basically considered as very potential hazardous heavy metals, and these we have seen that these are the elements which are basically present in the groundwater beyond the permissible limits. So, this is the data from 2018. We assume that this number of affected districts have increased, and it is possible due to the increased amount of industrialization as well as pesticides and other other anthropogenic activities which increases this concentration in the soil solution. We will see in details. So, let us consider this acid base equilibrium. Now, this the group of reactions covering the transfer of protons governs the acid base equilibrium reaction. Now, in this case the proton donor is an acid and the acceptor is a base. So, basically acid is equal, we can write that acid is equal to base plus proton. So, with the following equilibrium constant, so these reaction comes with the following equilibrium constant. This equilibrium constant is K0, which is denoted by this denoted by this ratio, where this K is acidity constant. So, this is the acidity constant and these parentheses are basically denoting the activities. So, this is basically the representation of acid base equilibrium. Now, given this acid base equilibria relationship where K0 is an acidity constant and these brackets are activities, this equation stipulates that for a given ratio of the activities of a particular acid and its conjugate base, the proton activity has a fixed value. So, if we consider that the ratio of a activities of particular acid and conjugate base is a constant, then the proton activity has a fixed value. So, this is basically the interpretation from there. So, in a system where we have a complex of 2 bases and 2 acids, the relationship becomes this, when acid 1 plus base 2 equal to acid 2 plus base 1, and the corresponding equilibrium under this condition can be represented by this K1 to 0 with the help of this ratio. So, ultimately we are getting the activities of base 1 multiplied by activity of acid 2 over activity of acid 1 multiplied by activity of base 2. So, this is for a single acid and single base, however, this is for complex of 2 bases and 2 acids. So, these are the equilibrium relationship between when these acids and bases are reacting together. So, this is in nutshell the acid base equilibrium. Now, we have seen that for a complex of 2 acids and 2 bases, the corresponding equilibrium is this one in our previous slide. So, we have already seen this is basically the ratio for this complex reaction. Now, remember that the soil solution being an aqueous system, H2O or water is the ever present acceptor. Now, for example, during the dissociation of an acid in the solution, these H3O plus or hydronium will be one of the dissociation products, and the acid strengths of this H acid relative to this hydronium ion will be a measurable parameter. So, in a dilute solution, the activity of this hydrated proton equal to this H3O plus, and the pH value characterizes the hydrogen ion activity. Now, under these all conditions, if we consider these conditions, so if we want to establish a relationship between pKa and pH, then we can establish this relationship that pH minus pKa equal to log of activity of base over activity of acid. So, this is a universal relationship. Okay. pH minus pKa equal to log of base activity by acidic activity. Now, you may ask, okay, sir, what is the pKa value? Now, to define a pKa value, this is a pKa value is one method which is used to indicate the strength of an acid. Remember that this pKa is the negative log of the acid dissociation constant or Ka value. So, if you consider the acid dissociation constant Ka, then the negative logarithm of this acid dissociation constant or Ka is basically the pKa value. Now, a lower pKa value indicates a stronger acid, that is, a lower value indicates the acid is more fully dissociates in water. Again, this Ka stands for the dissociation constant of an acid, and pK is basically the negative logarithm of this Ka value. So, obviously, a lower pK value means a stronger acid, that means more dissociation, that is the lower value indicates the acid is fully dissociates in water. For example, the pK of acetic acid is 4.8 while the pK of lactic acid is 3.8. So, using the pK values one can see that lactic acid is stronger acid than that of acetic acid. Since the pK value of lactic acid is less than the pK value of acetic acid, that means lactic acid is more strongly dissociates in water as compared to the acetic acid, and that is why lactic acid is stronger acid than that of acetic acid. So, we have covered the acid base equilibrium. Next, let us talk about the precipitation dissolution mechanism. Now, under various physiochemical conditions, a process of dissolution and precipitation of minerals in water occurs. It is a complex interplay between different physiochemical conditions. Now, this reaction is more common for the natural systems and plays a lesser part in the fate of the pollutants. So, although this precipitation dissolution is more common in natural system, however, it plays a lesser part in the fate of the pollutants. Now, the extent of the dissolution or precipitation reaction for systems that attain equilibrium can be estimated by considering the equilibrium constant. So, we have already seen what is the equilibrium constant. Now, remember that the precipitation of chemical can only occur at supersaturation, since dissolution ends only at water saturation. So, when there is a supersaturation only in that condition, there will be precipitation. Now, in the soil medium, the dissolution reaction is a heterogeneous chemical reaction. So, it is necessary to characterize the solubility in terms of a solubility product with an equilibrium constant, which can characterize the solubility as well as predict how solution variables can change the solubility. So, that is why there is a solubility product relationship, or we have already discussed the solubility product relationship in our previous lecture. So, I am not going to further discuss that in details. However, let us just consider the when this condition. So, when the dissolution in water of an electrolyte comprises a cation An plus and the anion Bm minus. So, this is basically the cation and this is basically the anion, which behaves according to the following reaction. So, they behave according to the following reaction, where these Am, Bn, S stands for the solid, then Ma in aqueous form and Nb in also aqueous form, where S and Aq stands for the solid and aqueous phase respectively. We have already know that. Now, the equilibrium condition is in this reaction, the equilibrium condition is Am, Bn, S equal to the. So, the activity of this solid will be the multiplication of the activity of this A in aqueous phase multiplied by this activity of B in aqueous phase, which gives the conventional solubility expression, that is KSO, which is basically the solubility product, and these brackets basically shows the activities. So, you can see the aqueous in the aqueous media, the activity of the cation when we multiply the activity of anion in the aqueous condition will get will give us the solubility product constant. So, this formula assumes that the activity of the pure solid phase is set equal to unity. Okay. So, this is the expression of solubility product when we are considering the electrolyte with an cation A plus, An plus and anion Bm minus and their dissolution in the aqueous phase. So, it is considered that a possible test to determine whether a solution is over and under saturated. I told you that there will be precipitation only when there is over saturated or super saturation. So, how to predict where there will be super saturation or when there will be precipitation or not. So, it is considered that a possible test to determine whether a solution is over or under saturated would be to check whether the dissolution free energy of the solid chemical is positive, negative or 0, and to compare that ion activity product. Now, we have already discussed this ion activity product, although, but I am going to repeat it here. So, we have to basically consider this dissolution free energy of the solid chemical, whether it is positive, negative or 0 as compared to the ion activity product. Okay. So, we have to consider this compare this ion activity product or IAP with this solubility product constant. So, the state of saturation of the solution with respect to the chemical in solid state is defined when this ion activity product is greater than the solubility coefficient, then or solubility product coefficient, then we consider it is oversaturated, and when there is an oversaturated, there will be precipitation. Okay. And when the IAP will be equal to the solubility product constant, then it will be in equilibrium or saturated condition. And when the IAP will be less than KSO, then that there is undersaturated and there is a possibility of dissolution. So, you can see here the condition for precipitation and dissolution. In case of precipitation, the ionic activity product has to be greater than KSO, and in case of dissolution this IAP has to be less than KSO. And when the IAP is equal to KSO, then we consider this is a equilibrium or in saturated condition. So, I hope that now it is clear. So, remember that oversaturation leads to the precipitation of the chemical, and a chemical substance can exist in more than one crystalline form, but except at a transition temperature only one thermodynamic stable for a given chemical composition of the system is possible. Remember that the metastable forms are more soluble than that of stable ones. Again, the chemical substance can exist in more than one crystalline form, but at a transition temperature only one is thermodynamically stable for a given chemical composition of the system. Okay. And these metastable forms are more soluble than that of the stable forms. So, if you see the relationship between the concentration and pH as given by Yaron et al. In 1996, this relationship will be, we can see this is the relationship between pH, concentration, and which condition it will be oversaturated or undersaturated. And in between this oversaturated and undersaturated, we can see the metastability limit and metastable conditions. Okay. So, this diagram basically shows that which the relationship between pH and the concentration and how they can manifest themselves in an oversaturated condition, as well as how they can be undersaturated and what is the metastable limit inside. So, we have already covered the surfactants in our previous weeks. You know about the surfactants. Now, it is very important to understand the effects of mixed solvents and surfactants. Now, remember that many of the potentially toxic organic chemicals reach the soil in a mixture of solvents or in formulation with dispersing agents. In this case, the dispersing agents are surfactants, and this is a surfactant molecule. As you can see, it has both hydrophobic tail, hydrophobic side as well as hydrophilic sides. The hydrophobic tail is basically oriented so that they can be directly in contact with organic immiscible form. It may be liquid form, it may be solid form. So, it is basically immiscible with water, hydrophobic phase, and the hydrophilic ends are arranged towards the aqueous phase. So, there is a specific orientation which helps them to act as a dispersing agent. Okay. Now, the objective of such formulation is to increase the solubility of an active compound in a solvent such as water. And remember that in a solvent which forms nearly ideal solution with another, and when the solubility of a third substance is limited to a low value by its crystal stability, the logarithm of its solubility is nearly a linear function of the mole fraction composition of the solvent. Again, I am telling it is complex to understand. So, in a solvent which forms nearly ideal solution with another. So, let us consider there are two solvents which can form an ideal solution with another, and when the solubility of a third substance is limited to a low value by its crystal stability, the logarithm of its solubility, if we plot the logarithm of its solubility, is nearly, we will see a nearly linear function of the mole fraction composition of the solvent. So, mole fraction composition of the mixture of the solvent. So, we will discuss this in more details in our next class. I hope that in our in this lecture you have gathered some information about the complex interaction between these heavy metals and their dynamics in the soil solution. You have gained some knowledge about acid base equilibria, and we have briefly covered the precipitation dissolution and their preconditions also. So, we will talk in more details about these effects of mixed solvents and surfactants in our next lectures of week 9 or module 9. Thank you very much.